Yeah, hi, it's Eric Lee again, and it's another one of my so-so videos put together. Um, I just wanted to make some correction in what I said last in my last two videos, and one of the things was uh, I pointed out this thing about symmetry of the universe, and I thought it was speaking about the actual shape of the universe, but in my simple mind and understanding of physics, I believe they're talking about the symmetry of quantum um, matter or particles. So, my mistake, and I told you I would make some instances, and hold on, my phone is ringing. Gosh. Yeah, sorry about that. The phone started ringing. And Anyway, I was saying that I think I misinterpreted what these equations were. It was much more complicated than just implying that there was a twist or something to the universe. But there is something interesting in my idea of what's going on, and um, I think it's the PBS series. They just um, brought up a video that dealt with pressurization and negative pressure. This idea that I was talking about um, in my whole lecture of videos or video lectures, I should say. And uh, they were pointing out that these two physicists they had already made a reference to this type of phenomenon, perhaps, which was an alternative to the Big Bang theory or further explanation of the theory, perhaps. I'm not exactly sure, but it's explained in my, I put it in the same Pinterest category that I put a lot of my videos, which is under time uh, on the Rubbish Writer. That's called the Rubbish Writer on Pinterest, and because I put a lot of like crazy stuff on there that's interesting. Um, but anyway, yeah. So this super symmetry is what they were, I think, aiming at with this equations, and that these two physicists here were talking about. Supersymmetry is like in the standard model, they have like six quantum particles that they've identified, and or no. I'm giving you. I don't want to give you wrong information. In the standard model, they have several. I don't want to give concrete numbers. They have several quantum particles, and to each particle, I believe there's an antimatter particle that correlates to each of the particles in this idea of um, the symmetry of quantum mechanics. And I don't want to even try to name the particles. I can't remember like every one of them, but anyway, that's not the point of what I'm trying to say right now. Is just I think I just totally screwed up in my interpretation of these calculations that are scribbled on here. And then what else did I want to say? But yeah, I still do think that you know the universe could possibly have a rotation of the observable universe. Or it may not. I mean, but I think it's probably finite, and what the matter is expanding into, mm, I said is just more of this unseen potential energy particles. It could be string particles or something else, and it's emerging into gases and whatnot. I guess maybe the Big Bang set off an entire chain of like events that uh, 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 these uh, particles are emerging from like a different multiverse. And that multiverse, I said, what defines a multiverse? Well, it's something our sensors cannot detect, or something we cannot even perceive. Maybe we can see the effects of it. Sort of like, one physicist said, like what air does. We can't see air, but we can breathe it. We can see, the wind blowing through the trees and whatnot around us, and the effects of it. But anyway, that's enough for the apology. Sorry if I made this like kind of dull moment for myself. But uh, what I was gonna say? Oh yeah, I was gonna talk about this interesting thing about these the shrimp that live under the ocean, and they live near these like the ocean floors here, and there's like all these like these jagged things that uh, uh, they're near volcanic activity, and there's these um, holes in these. They almost look like termites' nests or something, but it's not, from any kind of like animal building these structures. They just pop up out of the ocean, much like stalagmites, or uh, they just build this kind of like mineral or uh, mud like based structure, uh, and it emits this like these very very extremely hot water, and near, and I can't remember how hot it is. It's extremely hot. It's basically if I think you need to have like bathoscopes or like underwater submarines with robotic arms to even get near these things, and it would instantly boil any crustacean or animal that would be near these things. But what they found were these shrimp, these crazy shrimp, and they're like the size of like normal like big prawns or something, and they're crawling around down here, and they come near these boiling uh, 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 the boiling water, and they do not die. They don't boil. They don't cook, and I think the show that I'm watching was like years ago. So I don't know if they have an explanation for that yet. And I think they were saying it was kind of a mystery to it, but it's really no mystery. It's just physics at work, and basically, I thought like, well, I know why they're not boiling, because, well, first of all, they find these cauldrons of crazy fiery water that's coming out deep at some of the deepest points, uh, you know, on the Earth's seas, and and the compression. I think we were talking about the compression of like all matter. If we could just take a slice of the Earth's mantle, and let's say the ocean was just on this, like, kind of, this is exaggerated, I mean, you know, and the shrimp live somewhere here or down here. um, you know, basically all the what's happening is, um, uh, uh, the reason why they don't boil in this crazy hot temperature of the sea is, um, they're so compressed, underneath of this weight of all the entire ocean on top of them. uh, the gases have no way of escaping from their bodies. And if you notice, like, if you would just envision like a pot sitting on the stove, and you've got like this, water in here, and you set it on this fire on top of the stove, what would happen is you see all these bubbles forming, and let's say there was a shrimp in there, and this is at sea level. You would see like all the gases. Well, you wouldn't necessarily see the gases, but you would probably see some bubbling action, and all the gases would be coming out from the shrimp. And if you overcook shrimp, you ever notice how it gets really like harder, and that's from the release, not only of the gases, but along with the gases goes the fluid out from the meat of the shrimp. So basically, you get like overcooked shrimp, and you could say that sort of kind of happens when you burn like a good steak too. I mean, but we're strictly talking in water right now. So um, um, uh, that's why the shrimp doesn't boil. It's compressed to such a degree. For instance, like, okay, you have, let me give you a different example. Uh, like a diver, they get the bends, or decompression sickness when they come up too quickly from a very deep depth. I think it's beyond like 250 to 350 feet or something like that, and they have to come up very slowly and let their physical bodies adjust to the decompression. And um, so basically, what's happening is all the gases that are in the bloodstream will expand too quickly. Sort of like when you open this, like a can of soda here, and you pop it open. It was compressed, and then you release all the gases, and it just you know basically decompresses, and the gases that were squeezed into a smaller bubble, it just expands out, and starts coming out of the liquid. So it's like that. So it's no great mystery why the shrimp, um, they don't boil off. And one of the things that helped me kind of figure this out was an experiment that the cosmonauts did. Was they put one of their cosmonauts in this chamber, and they slowly introduced a vacuum. They pumped all the air out of it while he was in there, and I think he had a very basic tube going into his nostrils or something like that. Nothing really sophisticated, because they wanted to see what it would do to, like, you know a naked human, basically. So what he started complaining about, as they slowly decompressed this chamber and made it into a vacuum, was, he said he started feeling that, like, his tongue was boiling. His tongue felt extremely hot, and the the gases in his body were starting to basically try to come out through his tongue, and the tongue is one of the most sensitive parts of the body, so he could feel it in his tongue first. So they had to quickly, well, not quickly, but uh, reintroduce atmosphere into this chamber. And I was like, gee, that's very interesting. So basically, when you see depictions of, in science fiction movies where, the guy loses all the air and decompresses out in space, you know, um, basically they're boiling off all their uh, uh, gases in their body, and the liquid, depending on whether you're in direct sunlight or in darkness in space, you would either freeze, or you would literally cook off. So it's very kind of freaky stuff. But um, what else was I gonna say? It's a lot of crazy things. And then so uh, this compression of matter. Again, it's like you could have like basically three planets, or um, one could be a planet, one could be a black hole, whatnot. But depending on the density of these particles that basically uh, come into the center, and if you watch my other videos, it's like they go in like this to the center of each spherical shaped star or planetary body, and they create distortion around the um, astronomical planet, star, or even I guess black hole. I'll explain that in a second. But I came up with this thing called it's called a let me see if I can even get it right myself. Gravitational vector, gravitational vector angle acceleration. Yeah, it's called gravitational vector angle acceleration. And what that means is, like, depending on how dense um, the astronomical body is, such as a planet, uh, you know, how dense it is and how much mass it has, you've got like a uh, uh, like this angle of momentum or acceleration. And let's say this is for Earth, would be like that. But if this was like Jupiter, then the gravitational angle of acceleration would be more slimmer, like at a more steeper, less of an angle. The distortion would be more, what would you call it? Acute. The angle would be less here. You got the wider angle here. So basically, it's distorting less of the matter which is inside the planet. Like I was demonstrating, if this was like dirt and all the people and atmosphere and everything in here, basically the wider the angle of the gravitational angle of distortion, or compression, I should say. The distortion leads to the compression because it literally warps the space and time around these astronomical bodies, and it's all in the layering. It's like What I mean by that is like, okay, on Earth, let's go back to Earth. You see, okay, here you see, let's say if you were to layer the Earth, you would see the core here somewhere, which is supposed to be made from iron and heavy metals. And then you would have like this like magma layer or plasma layer, whatever you want to call it. I'm not a geologist, so excuse me if I don't know all the different layers. And it's just layered all the way through. Even the ocean is layered. The thermal layers. There's like some layers of the ocean. Um, they have like a much faster current, and it's like sandwiched in between. Two layers that. I mean, just it's just some what would you call it, sandwiching going on with this. I can't remember what they call that current. It's so fast. If you get caught in this current, it can just like pull you, you know, while you're scuba diving at these depths, or if you're in a submarine, a small submarine, it can like catch you off guard and drag you way off course. But anyway, you get what I'm saying. It's just the atmosphere is layered. Uh, uh, you can go on and on with the layering example, and you can go all the way out to the Oort cloud, and then beyond the Oort cloud, there's a huge dome. And yeah, this is in 3D. If you I'm just drawing this in 2D, but this is of course spherical, and these layers are forming in like dome fashion, and um, you know some of the material, like the heavy metals, make it back to the surface. I think because, well, this particle that I was talking about that actually does the distorting of space time, when it like is gathering around this or surrounding the planet, because we're accelerating. We're not accelerating. Well, yeah, we're accelerating through space, and at first I thought it was coming to us, but I think we're going through this sea of these particles. It has a tendency to cluster around in a like a spherical manner in layers. And I said the astronomical unit is one example of a kickback of this when the energy literally comes towards the center of the Earth, let's say, in the center. There's quantum tunneling, and it loses a little bit of the energy of distortion. And then when it goes with Newton's theory of, for every action there's an opposing action, then you find that some of the heavy metals and whatnot are forced back through different actions, like volcanic activity. You see volcanic activity, things like um, coming out this way, and you see certain forces. Not only the compression of everything coming, down on the on this angle of gravitational angle distortion. Uh, you see also energy which is released back up, and that is why I said that, like, the moon could be accelerating away from the Earth's orbit, as the scientists claim, and because I thought that was kind of like counterintuitive to orbital decay and all of that, as I explained before. But that would explain why, you know, basically the moon is achieving like escape velocity, because that's the only way you can establish uh, uh, an astronomical body moving away from from the Earth itself, like something as massive as the moon, because it has no rocket engines, you could say, well, is it centrifugal force? Well, not really. I mean, has to be something else. Um, but it's the way the gravity behaves with this potential energy or string matter or whatever is pushing away on this. But the funny thing, going back to this gravitational uh, vector, gravitational uh, vector angle velocity, gravitational vector angle velocity. I had it written down somewhere, but it's not, I don't know. I couldn't find the page. I have so many notes. But this the angle of velocity, of course, in a when it comes to, let's say this is a black hole, it wouldn't be like any, even the slenderest of angles. It wouldn't even be like that. I think it would just turn into that, and because the angle would just come together into just one, like, as they call it, a singularity, and it would just like uh, any matter, any type of well, yeah, any type of matter would just be smashed into just one singularity. And as I said before, it. I think black holes are what produces this mysterious energy to be found in space. And I said that the entire cosmos is filled with this energy. And energy is mass, according to Einstein's equation. So, um, anyway, yeah, so these black holes grind up everything and they spit it back out, and they actually have things called white holes. And I explained all that in the other video. But I just wanted to just explain about the non boiling of the shrimp, why that they don't cook off in the deep oceans, because they're being held together by the actual compression of matter all around it, which is the ocean. And I mean, there might be other physiological, like chemical reasons too, but that's the main thing. Is the gases are not allowed to escape from the flesh of the shrimp, and it retains the fluids inside as a result. But it all has to do with physics, and again, it's a gravitational vector angle velocity. So it's a term I came up with myself. If somebody has already come up with something like that, I do apologize if I did, use somebody else's idea. But it's something I just totally made up. But what else did I want to mention? Uh, so yeah, I mentioned the PBS series, and these two guys were talking about negative pressure and this and that. I wanted to cover that, and I think that's pretty much it for this video. And oh, there's a brilliant physicist. He works with the Hadron Collider. He's a British physicist. He's got his own YouTube channel now with the Royal Institute of England, and his name is Harry. And I put that on my Pinterest too, and that's a very, very interesting um, video I put on there. And what he explains in detail, I kind of guessed in my own crazy way. by just tidbits of information, like I said, just uh, from books and whatnot, and from some documentaries. And basically, it was I was stuck on this rickety sailboat for almost a year, stranded. We we had lost everything, and basically, lived by my wife, and our kids were stuck on this boat. We, it really kind of put a crazy perspective on life, and I was just trying to find meaning to everything, and had a lot of time to think about, you know, various things. And one of the things that kind of held my mind together a bit was thinking about physics. And so this happened years ago, and things are improving slowly. So um, anyway, it just, you know, that's a whole nother story. I could write a book on that. But anyway, yeah, you just have to keep a sense of humor, and you know, whatnot. But that's where all these ideas started, like, just kind of congealing in this, goofy head of mine. And I I hope this kind of these ideas have some merit. Uh, well, yeah, they do, because I mean, even what this physicist Harry said confirmed a lot of my suspicions, and you know, I see, like, I'm on the right track to explaining a lot of stuff, and uh, in quantum mechanics, um, what do you say? I'm getting confirmation that I was definitely on the right track. It wasn't like I saw these videos and then and basically, um, made my assertion. It was the other way around. These videos popped up on my YouTube just recently, and um, I don't know, AI or somebody's watching me. I don't know. uh, you know, but it was very interesting to get these videos, and I was like, oh wow, I was on the right track, and I think I do have some differences in the way I in my theories, but overall, if you watch and listen to what a lot of these real physicists with PhDs are saying, it's you know, I think, without any false modesty, I can say I think I did a pretty good job of conceptualizing uh, uh, generally quantum mechanics and relativity, and kind of trying to put it together somehow. And I think the next thing I want to try and to look into is quantum field theory. That sounds very interesting. So anyway, like I said, it's probably not the last video I'm gonna bother you guys with. I just appreciate any views, or if you like what I'm saying, or even if you don't like what I'm saying, you can put like or dislike. But any reaction would be appreciated. The comments, I don't even know how to turn them on. That's why I don't have any comments. And probably half the comments would probably be very, like, crazy stuff, anyway. So I don't even know how to turn them on. That's the honest truth. But anyway, I hope you guys liked this video, and I guess I'll see you guys next time whenever I get another inkling or inspiration to make another video, I'll post it, and I'll put it on my Pinterest. And it's the Rubbish Writer. That's what my Pinterest is called. And it's usually I put it under time, and then I have another section called My Rubbish Videos, where all the videos I create, I is this section called My Rubbish Videos. So thank you for listening, and bye bye, and keep your sense of humor.